In this slide, we'll visualize the complex exponential e to the power of j 2 pi over n kn. And what is this? I mean, this is the most important signal. Basically, it is a complex exponential that is rotating. And we're going to draw it for you for n equals to 100 and for different k. So what you see is that this is a 2D representation of the complex exponential, and if k is equals to 0, then what you will see is that it's ej0n, and in ej0n, even as n increases, the phasor remains stationary. This is the real part of ej omega n, and this is the imaginary of ej omega n. So you see that the real is 1, because this is the real axis, and this is the imaginary axis. So the real value is 1 with imaginary 0, so this is all 1 and this is all 0 as n progresses. So this is time n. Now, we then choose different different omega. So this is omega equals to 0.02 pi. So you can think of it as 2 pi divided by 100. So this is 0.02 pi. So this is 2 pi over n, because 2 pi divided by n, and n is 100. So how does this look like? Well, you actually see that the phasor is going to rotate anti-clockwise, and it will take 100 samples to rotate one round. And in the cosine, which is the real part, it will also take 100 samples to rotate one round, and this is the imaginary. It will also take 100 cycles to rotate one round. As k increases, so this is k equals to 1, and here is k equals to 2, because you will see 0.04 pi. 2 times 2 pi is 4 pi, divided by 100 is 0.04 pi. So now you'll see that the phasor is moving in a bigger angle. So if you carefully look at here, this angle would be 0.04 pi, as indicated by this value here. This is what it means. And what you'll see in the real and imaginary is that this guy sticks to, it will then, in 100 sample, makes 2 round. And the sine also, in 100 cycle, it makes 2 round. So as we increase again, this is k equals to 3. Now the angle again becomes bigger and bigger. This is 0.06 pi. So every step, it makes 0.06 pi, and therefore in 100 samples, you make 3 rounds. 1 round, 2 round, 3 round, or 3 cycles for the cosine, 3 cycles for the sine. So now you will see that you will understand what does ej2 pi over n kn means. Now, the interesting thing is the k. K tells us how much faster, how many harmonics with respect to 2 pi over n. So 2 pi over n is the fundamental frequency. And when k equals to 1 is the fundamental frequency, k equals to 2 is 2 times the fundamental frequency, 3 times the fundamental frequency. So where does this signal appears? Well, in the last figure, we realized that this is omega. And here, at this point, is 0.2 pi. So, and then we know that this here is equal to k equals to 10, because we're going from 0 to 100 in the previous example. So actually, the horizontal axis shows us exactly where k is, the kth harmonics of the complex exponential ej2 pi over n k small n we're interested in. Okay, so this is the interpretation of this complex exponential with respect to the horizontal axis of the magnitude and the phase response. Thank you.